Good morning.
Morning.
Good morning.
All right. Okay. So we're going to be talking about thermodynamics today. We'll start out the Gibbs free energy. Let's take a look at the schedule here. We'll see how far we're supposed to get today. Yes, up to calculating K. Okay. So today we'll be focusing on Gibbs free energy, which will allow us to determine whether or not reactions will go on a spontaneous basis. And what we use to do that is to figure out delta G. And the equation that we use here is delta G equals delta H minus T delta S. Now, delta H is something that we are somewhat familiar with, or should be, and that's enthalpy. That's the heat of reaction. And what this allows us to do is determine the energy difference between the products and the reactants. Now, that's all it does, products and the reactants. So when you're looking at, let's get rid of this here. When we're looking at enthalpy, I do like to use these energy profiles to explain this. And we talk about two cases. So we have energy on this axis. We have a pathway, reaction pathway on this axis, or reaction coordinate. And an energy profile always starts at the reactants and goes towards the products. So I'm going to show you two different cases here. We've got this one where the reactants are here and the products are below the reactants, and this one where the products are above the reactants. So this represents what we call the activation energy. And we looked at this a bit in test one. And the delta H in both cases, and it doesn't matter whether it's the products are above or below the reactants, the delta H represents the difference in between the two. And it's not determined at all by the activation energy or anything else that's going on in the reaction between the reactants and products. All that matters is the difference in energy at the beginning and the end. So that's delta H. Now the delta H is determined by the equation that we learned about back in Chem 1. Delta H naught of formation of products minus the sum of the delta H of formation of the reactants. So it's always products minus reactants. So you can see here that if we did P minus R, it would be a negative value because P is smaller. And here, if we did products minus reactants, you can see that it's going to be positive. on the bottom one because the products are bigger than the reactants. So we call this one exothermic. This is because the negative represents an energy lost, and that would be released usually as heat. And then we've got the other one, this is endothermic, which means that energy is drawn into the reaction from the outside. Now it turns out, because the products, in this case, the exothermic case, the products are less than the reactants, that means that they're more stable. So that means that if we're just purely looking at enthalpy, generally speaking, exothermic reactions are more favorable than endothermic ones. Only for one reason, and that is that the products are more stable than the reactants. That's all. The products are more stable than the reactants. Does anybody have any questions? Okay, so that's enthalpy. I think you're somewhat familiar with that, or should be. Now, what you might not be that familiar with is the concept of entropy, but this also is part of the delta G equation. You can see it's delta G is delta H minus T delta S. So what is entropy? Entropy is the tendency of systems to become more disordered. But really, it's a bit simpler than that, in my opinion. Let's say you've got a situation where you've got, say, I don't know, even just two gas molecules in a container. And in another situation, we've got a situation where there's three different gases in a container and there's more molecules. What I would want you to understand is that in the right-hand case, there's many more possibilities to arrange those molecules than there would be in the case where there's just two molecules in the container. Really, that's what it all comes down to. It's possibilities for arrangement. And the thing is that the universe will focus on situations where there's more possibilities for arrangement. That's all. You know, that's all it comes down to. How many possibilities are there for arrangement? And that can actually be measured. That's entropy. Now, the entropy is also figured out by the products minus the reactants. So delta S, the change in entropy, delta S naught, is equal to S naught of the products. So the entropy of the products minus the entropy, let's make that sum of the entropy of the reactants. So products minus reactants again. Now there's a little bit of a difference here with the signage, and that means that, and I'll just pull this up on the slide here because I've got it explained here. That if there's more energy on the product side, sorry, more entropy on the product side, then that's going to mean that delta S is a positive value, because that means you've got a big number minus a small number. And if there's more entropy on the reactant side, then delta S will be a negative value. So what I was saying is that reactions tend to favor situations where we're creating more entropy, where we're creating more possibilities for arrangement. So situations where the products have a bigger entropy than the reactants. That's what we're aiming for here. Does anybody have any questions? Okay, so a couple of common sense rules that we can talk about with regard to entropy. First of all, the entropy of anything not at 0 Kelvin will always be greater than 0. And because we can't ever get down to 0 Kelvin, it effectively means that we're always going to have some kind of entropy. Entropy of gas is going to be greater than ions, is going to be greater than pure liquids, is going to be greater than solids. So let me explain the difference between ions in solutions and liquids. A liquid would be a pure liquid like water or bromine or something like that. Whereas ions in solution would be a situation where you've got ions like, say, Na plus and Cl minus in an aqueous solution. So that's going to be more entropic than just pure liquids because there's going to, again, be more possibilities for arrangements. Same with gases. And I think you've all seen solids as well. So, I mean, I'll just very quickly draw a couple of diagrams for that, but I think you're pretty much on the track of what I'm talking about here. So let's say you got solid. Solids usually look something like this. There might be a little movement around, but they're pretty much stuck where they are for solid. For liquids, oops, they're all moving around each other. So there's a bit more going on than with solids. And with gases, they're going every which way. Now, the difference between a liquid and a gas is fairly simple. It's just that with liquids, these are touching. And with gas, they're not touching. So that's why there's going to be many more ways that we can arrange things in gaseous form than in liquid form. So that's, I think that's not too bad. Does anybody have any questions about this? Okay, let's look at some calculations. And I'm going to skip.
Gibbs free energy.
Sorry.
Could you go back to Gibbs free energy? I haven't written.
I'm sorry, I didn't hear you. I didn't hear you.
Could you go back to Gibbs free entropy, free energy, and entropy rules? I haven't written that down.
Oh, okay, there you go. Well, you know you have access to this too. This is the printed PowerPoint notes. It's in the test 3 folder. Now the other thing here I didn't mention is bigger molecules have more entropy than smaller molecules of similar composition. So an example of that would be O3 versus O2. And because of that extra O in the molecule, again, more ways to arrange things, more ways to angle things. So yeah, that makes sense as well. Yeah, okay. I will, let me think. I'm going to skip over this predicting the sign of delta G for now, and we'll focus first on the calculation of delta G and K. Then we'll come back and we'll look at how we can predict the sign of delta G by not doing any calculations. But we'll do the calculations thing first because that's what I've got down in the syllabus here. Okay. So we're going to focus on how we're getting the delta G value, and the delta G formula that we talked about was delta H minus T delta S, and you can see that's listed here. So that means we have to calculate delta H and S. You'll also notice that in the question we're given a temperature, that's going to be T. You have a temperature given is in degrees Celsius, but anything that we're working with needs to be converted to Kelvin, because everything has to be in Kelvin at the end of all of this. So how do we find these values? Well, they're in a table, and it's in the table, it's in the back of your book, but also a table that I have here Let's go back to that. In the test 3 folder, and you'll find it under this link called tables. So I'm going to go ahead and show you what that looks like. There you go. So this is the delta H and S values of all these different substances. You'll notice that in a lot of cases, not all cases, but a lot of cases, the delta H of formation is a negative value. Now, what is the delta H of formation specifically? The heat of formation is pretty much what it sounds like. And what it is, it's the energy gained or released when a compound is formed from its elements in their natural state. That sounds complicated, doesn't it? Okay, so the delta HF naught for any element in its natural state. Yeah, I know it's worried you because you're worried about how you know if something's in its natural state or not, but I'll get to that in a second. Is going to be 0. So that makes sense because you can't make an element from anything. The element is pretty much the lowest form of anything. It's the building block of anything that we have. So to give you an example of what I'm talking about with heat of formation, let's just look at something fairly simple. We'll look at CO2 gas. So what elements, this isn't a trick question, by the way, what elements are used to create that compound? Anybody want to guess?
Carbon, oxygen.
All right, so carbon and oxygen, that's fair enough. So we'll say C. But but what's carbon in its natural form? Well, it's actually solid graphite. Specifically, graphite is what's in your pencils, by the way. And does anybody know what the natural form of oxygen is?
A gas.
It's a gas. Specifically, though, O what?
O2.
O2, so O2 gas. All right, so you might be worried, oh gosh, I don't know all these natural states. Well, you can get it off the table because you can see here that anything that has a 0 is going to be in its natural state. So aluminum solid, that's going to be aluminum in its natural state. Let's take a look at oxygen. You'll see this here. Oxygen, see, it's in alphabetical order. There we go. You've got O, that's not 0. O2 is 0. O3 isn't 0. So you can tell exactly what the natural state is by looking for whatever's 0. But my point is, if we look at CO2, see if I can find CO2 here. There's your carbon graphite there. See, carbon graphite is 0. CO2 is negative 393.5. So that is the heat of formation of CO2 gas. What that means is that that's the amount of energy it's released because it's negative, right? So it's a negative, that's the amount of energy that gets released when we mix carbon and oxygen together to form CO2. So that's what the heat of formation exactly is. And as I said, we just get those directly off the table. Obviously, you don't have to memorize any of those. Does anybody have any questions? You'll also notice in the same table, we've got the S naught values. So these are the entropies of the individual substances. You'll notice that for elements in a natural state, they're not zero. The other thing you'll notice is that unless we're looking at ions, and ions are a special case here, the entropies do tend to be mostly positive. And you can see that as you go through there. But ions in solution tend to be negative for some reason. I'm not exactly sure why that is, but I think it's got to do with the fact that when you have an ion in solution, then it arranges solvent molecules around it, which tends to lower the entropy overall. So I'm not exactly sure of the reason, but that's an observation that one can make just by looking at the stuff in the table here. The other thing you'll notice is if we're just looking at entropies, let's say just comparing bromine liquid and bromine gas, you can see it's 152.2 for the liquid and 245.4 for the gas. So we talked about that earlier, that entropy of gases is going to be more than liquids. So that's an example of that. The unit is joules per mole per Kelvin, which you can see on the table here. So that's obviously not something you have to remember because it's always there. So you'll see that when we're doing the calculation, they're kind of similar calculations. So if I wanted to do this one here, it's 4 times the product minus 1 times S8 minus 4 times Cl2 gas. Cl2 gas is 0. That's why I've just got 0 here. And we end up getting, for this one, negative 175.9 kilojoules per mole. And those are just values that are taken off the table. So let's have a look here. Sulfur, see we've got S2Cl2 somewhere here. Here it is, S2Cl2, Vg minus 18.4. The S8 gas, that's there as well. And the Cl2 is back in chlorine. But as I said, we know that that's going to be 0 anyway. And chlorine's down here, yeah, here it goes. All right, and that's where we also get our S naught values as well. So to get the delta H values, we go ahead and we take all the products, we subtract out the sum of all the reactants here. My recommendation is to put the products and reactants in square brackets and put a minus between them, and to handle the calculations separately. But don't do any rounding until the very end. When you're looking at significant figures, the significant figures will always be based on the number of places past the decimal, because these are strictly addition subtraction calculations. Now, I know you're looking at this and you're saying, well, hang on, what about this? This is 4 times, right? And that's a times. That's multiplication. It actually isn't, because the 4 here and the 4 here are counting numbers. They're part of an equation. We don't use a fraction of a molecule of Cl2 in this. We need 4 complete molecules of Cl2 to get this reaction to go. So instead of it being 4 times minus 18.4, it's really minus 18.4 plus minus 18.4 plus minus 18.4 plus minus 18.4. Just added to itself 4 times. So what that means is we just look at the number of places past the decimal, and that tells us how many places past the decimal we'll have in our answer. But as I said, don't round as you go, just round at the end. Does anybody have any questions about this calculation for delta H? Okay, we do something similar for the delta S as well. And again, we just pull these values directly off the table. We give them the unit that's on the table, kilojoules per mole for delta H and joules per Kelvin per mole for delta S. Does anybody have any questions about delta H or delta S and how we're getting those values? Okay. So then once we have delta H and delta S, we can get delta G, and delta G is going to be delta H minus T delta S. Now we have a bit of an issue going here. I mean, if you look at the units, we've got kilojoules per mole for the delta H, and we've got joules per Kelvin per mole for the delta S. So we don't have something that matches here. We've got kilojoules and we've got joules. So when we're doing the delta G calculation, here's what we do. We've got our delta H, which is what we put in here. Then we do minus the temperature gets converted from 25 to 298 using 273.15. But again, it gets shortened out to 0 decimal places. So 298 K from 25 degrees Celsius. Times the delta S, which we calculated, that's fine. But then we also do a conversion here where we take the joules and convert them, sorry, the joules and convert them into kilojoules. So you can see I do that exactly here. 298 times 3.8 times 1 kilojoule over 1,000 joules. Now that's to get those joules into kilojoules. You'll notice that the kelvins cancel as well as we do this, and we're just left with kilojoules per mole. So right now we have something where we can match and actually do a subtraction. You'll notice that the part in parentheses here is pure multiplication. So we do actually need to get the significant figures for that part separately because we are mixing operations. This is multiplication inside the parentheses, and then we've got the subtraction on the outside as well going on. So that's how we end up getting this minus 177.0 kilojoules per mole for the delta G value. Does anybody have any questions about that? It's especially important to note the kilojoule-joule conversion we have to do in that part of the equation. Does anybody have any questions?
I'm a bit confused. We get 298 for Kelvin, but we have 25 degrees at the start.
So that's in Celsius, but the temperature has to be in Kelvin.
Yeah, but wouldn't that be two significant figures? Nothing.
No, because let me show you. So the temperature is going to be 25 degrees Celsius plus 273.15, right? That's to get into Kelvin. Now this is an addition.
It's addition.
Yeah, so there's no places past the decimal, so it comes out to be 298K. Is that okay?
Yeah.
Okay. Any other questions about this delta G calculation? How we're getting any of the values here? So again, this is something you just want to practice, right? You just want to practice this and make sure that you're getting those values and understanding how you're getting those values. So by doing the extra credit, that's really helpful because you actually have to use the tables I give you in order to get those answers. Let's see, yeah. Okay, any other questions about delta G? All right. There is one other thing we can calculate too, and that's K. Now, it's, when I talk about K for this reaction here, the equilibrium constant, which we've obviously done a lot of stuff with. K for this one would be S2Cl2 to the 4th over S8 times Cl2 to the 4th. So that value there, the equilibrium constant, we can actually calculate that using an equation. Delta G naught equals negative RT ln of K. So what we're doing there, and I'll go ahead and show you the math for the rearrangement there. So this is an equation you don't have to memorize. I give it to you. So what we're doing is we're trying to isolate K here. So we know that ln of K, that's natural log of K, is going to be negative delta G naught over RT. That means if I want K, then it's going to be the inverse natural log, which is either the power of negative delta G naught over RT. If you look on your calculator at the ln button, and then you look above it, the second function of the ln, what you'll see is that it's e to the x, right? E to the x is what it is. So that's how you get rid of the ln part. You do the inverse natural log to both sides, and that's why it's e to the power of negative delta G. So I haven't got that written down here on the slide. I've just got inverse ln, which is the same as e to the x, right? So it's e to the x. So what we do here, we've got a value of R, and the value of R is 8.314 joules per mole per Kelvin. So that's again a value you're given, you don't have to memorize that. So what we do is we go ahead and we substitute those values in. We've got delta G is kilojoules per mole. We've got the R, which is joules per mole per Kelvin. We've got T, which of course is Kelvin. But again, we've got this issue with the different units. So the kilojoule needs to be converted into joules. And we do that on top here. That's why it's kilojoules times 1,000 joules over 1 kilojoule in order to get that into joules. And that way we can end up getting the value we have down here. What I'd like you to do, I'd like you to, first of all, understand this negative business here. The equation is minus delta G naught. Now, delta G naught is minus 177.0. So what that means is that we do a minus of a minus because the delta G itself was negative. So that, of course, is going to be positive, that negative. I'd like you to put this in your calculator and see if you come out to the same value as I do down here. So go ahead and do that now, please. All right, did anybody have any issues entering that in their calculator and getting that answer? Okay.
No.
That's good. All right. Well, that's good. Well, that's pretty much what I had wanted to cover today. I'm going to go and show you some of the resources that will help you to study for this. So let's look at, first of all, the enthalpy folder. So this is where you'll have to use the tables that are in the test 3 folder. You can't use tables from anywhere else. They do have some slight variations in values across tables. So it's important you use the set of tables I told you about. But you would use the tables in the same way as I've told you by looking at the equations that we have here. All right, so it's the same kind of deal. You just look them up and then find the difference. It is checked for significant figures here as well. So be careful and make sure you use your smallest decimal places in order to get those answers. Anybody have any questions about the enthalpy practice quiz? Again, you're just using these values here on this table, specifically this table though. Okay. I have a similar quiz for entropy as well, conveniently. Oops. And you see it's the same situation. All right, so that's good practice. All of that's extra credit. All of that's extra credit. I'll show you in a minute what it looks like on the test as well. Looks a little different, but it's the same kind of thing. And then we've got the Gibbs free energy, that's a delta G. And I also have a little worksheet here as well in this folder to calculate delta G and K that has that gives you the answers as well below those. So that's something for you to work on if you want some extra practice. But here's the Gibbs free energy practice quiz. And this kind of looks more like what it looks like on the table, on the test. So I give you this sort of fake equation here. Your mission here is to calculate delta H and to calculate delta S and then figure out delta G and put in the answer. And you see it varies as we go through these. So that's something to look at as well. So that's fun. And there's a K calculations quiz as well of similar ilk. And in this case, you've got to be a little bit careful. You're calculating PK. So remember what that means. Take the negative log of the K value in order to get your answer. That doesn't have any units on it. But you'll do something very similar to what we just did. Calculate delta H, calculate delta S, calculate delta G, and then come up with the K value. So it's all really good practice to get what you need at the end here. Does anybody have any questions? Okay. Let's take a look at the test here. So you'll notice that, first of all, I do have a link to the on-lock calculator here, and what I strongly recommend is that you use this with the practice test. So open this in a new window. So you can just right-click on it, open link in new window, and then use it next to the test while you're actually doing the test. Because you'll actually have to use it with the real test as well. So just keep that in mind. I do give you these equations here, the Gibbs free energy equation and the delta G equals negative RT ln of K. I think I give you the R value in the actual problem, so I think you'll see that. So I'm just moving this over here. I'll move it over here. Here we go. So question 1, calculate the enthalpy. Again, you've got the fake reaction here. You'll get the delta G. You'll get the delta H by just doing the equation. You'll notice that you don't really have to look anything up because it's all given to you. Same with the entropy, do the same thing. Gibbs free energy, do the same thing with that. And the K, you do the same thing here, except we're looking for PK. And I'll give you the R value in the actual question. And the equations are back up here at the top. All right, does anybody have any questions about any of that stuff that we talked about just now? So, you know, one thing I talk about, I talk about the need to make sure that we're not leaving all the review and stuff till the last day, to the day of actually, to the day when the test is due. And I think a lot of people have been doing that. And, you know, this is a prime example of something you can definitely get your teeth into now. You know, you can get that extra credit stuff done now. You can start doing problems 1 to 4 now, so that you can end up getting familiar with the material now, rather than having to review it on the last day, which is not something you really want to have to do. But, you know, I can say that till I'm blue in the face. I don't have any control over what anybody does or how anybody ever uses their time or how wisely they use their time. So, you know, that's not something I can control. But anyway, that's my 2 cents right there. Well, if I look at the syllabus, this is what I had wanted to cover today. I don't think I need to cover anything else. Does anybody have any questions? Does anybody have any questions? I know we're done kind of early. I'll just make sure there was nothing else I had to cover. I think that was it. Yeah. Yep. That's it. And that's all I had wanted to do today. All right. Anything else? Anybody got any other questions? All right. Well, you got your work cut out for you. Practice, practice, practice. Nobody can sit here and can complain that they don't have the resources. So hop to it. That's all I can really say. All right. So for some of you, I'll see you in lab in about 45 minutes. The rest of you, good morning. If anybody wants to hang around, they may. The rest of you, ciao.
All right. Thanks. Bye.
Have a good day.
Professor, I'll see you Thursday.
Georgiana, do you need anything?
Nope, I'm good. Thank
Okay,
you.
no worries.